one last rule that I want to show you, one last transformation I want to show you, involves looking at the Laplace transform of f of t over t. Just like before, it's going to be easiest if we evaluate this kind of in the reverse order. So I'm not going to explain how people first discovered this necessarily, but I want to just give you a proof. And so what I want to do is I want to look at the following quantity. We're going to look at the integral from s to infinity of the Fourier transform of f, the Fourier transform capital F, du. And this Fourier transform capital F is nothing more than the integral from 0 to infinity. I forgot the integral sign here. So from 0 to infinity, e to the negative st, f of t dt. And you know what? I shouldn't have used s. I need to use u, because that is the variable that we have. So I need to write that as that integral. And again, I'm going to do something completely unjustified, but it turns out it's fine. I'm going to switch the bounds of integration, and it turns out that we can do this with no problem based on Fubini's theorem in Calc 3, right? If you have basically if you have a nice enough function, you can switch the order of integration. Here, notice that switching the order of integration really is fine because our bounds for t don't depend on u, right? So our bounds for t just go from 0 to infinity. They don't depend on u. Everything is totally fine. So we're going to integrate now from 0 to infinity first, and then, from 0 to infinity on the left, and then from s to infinity. And then our integrand is going to stay the same, e to the negative ut, f of t, except we just switched our du and dt, so I better write du dt. Okay. That is what we get if we switch the bounds of our integral. The next thing that I want to do, is I want to look at, so I'm just going to rewrite this. Notice that this integral is with respect to u, so I can bring this f of t out, because that f of t is a constant with respect to u, so that this is the integral from 0 to infinity, f of t times the rest, which is the integral from s to infinity, e to the negative ut du times dt. And it turns out that this integral e to the negative ut from s to infinity, we can just straight up evaluate, and let's see what we get. We're going to get, let's see, so we're integrating with respect to u. That means that we're going to end up with negative 1 over t, e to the negative ut is u goes from s to infinity dt. And so let's see, as t goes to infinity, this whole thing is going to go to 0. So as t goes to infinity, we get 0, so that part's nice. So we're going to end up with f of t, so we're going to have 0. And then minus, let's see what happens when t is s. I'm sorry, when, not t, u, we're differentiating with respect to u. So as u goes to infinity, this is still going to go to 0. As u goes to s, we end up with minus 1 over, so that's going to be plus. Remember what's happening is we're subtracting. I'm doing this slightly out of order here, but as u goes to infinity, this is 0. And then we're going to subtract what we got when we plug in u equals s. So that's going to be negative 1 over t, e to the negative st, and then we still have our dt. And if we kind of unwrap everything and look at it, it turns out what we're going to end up with is we have the integral from 0 to infinity. This is going to turn out to be a plus, right? So plus e to the negative st times f of t over t dt. And it turns out that is exactly the Laplace transform of f of t over t. Okay, and so I think it's worthwhile just to point out, so I just want you to remember that f of t over t is, I just want to talk about the assumptions that we just made there. We just did a bunch of things there, but I just want to talk about the assumptions that we were just making. And it turns out what we really need, if we think about this, is we need this f of t over t part to be well behaved, not at infinity. Actually, we don't care about that, because as long as f is exponentially bounded, it's fine. And dividing by t is not going to matter as we go to infinity. But the trouble part's actually at 0. So these are all valid operations as long as, right, so long as this function is nicely behaved at 0. So as long as the limit of f of t over t exists and is some finite number. Okay, so that's the mild assumption that we need to make. We don't really need to think too much about that, but that is that transformation there.